Hello, Astronomy. Mr. Janowski. This is part 8 of the Chapter 13 slides. In the last part, we talked about binary stars and why they're so important to astronomers and different types of binary stars. In this part, we're going to talk about something called a Hertzsprung-Russell diagram, which is a very important way astronomers have of organizing stars and comparing them and just thinking about them in general. So let's get started with that. So first, to review what we did last time, why are binary stars so important? The most useful thing about binary stars is having binary stars gives us a way to figure out stars' masses. So that's very, very useful because knowing the mass is the key to understanding lots of things about the star, how long it's going to live, where it is in its evolution, where it is along its lifetime, things like that. So what do we call binary stars that are so close together that they actually touch, orbiting in contact with each other in a common envelope of gas? We call these contact binaries. Well, they're in contact with each other, so that seems like a good name for them. So instead of having single spherical stars, you're going to have stars that are kind of elongated, so they look a little bit squished. That's because of their gravitational attraction to each other and tidal effects that are actually kind of connected. So it sort of looks like a peanut in a sense. So those are contact binaries. One of the types of binaries we learned about. So the other binaries we learned about. So what do we call the binaries whose orbital motion around each other can be seen by comparing images taking a few years apart? These are the visual binaries. So if you can, with a telescope, actually see that the stars are separated and you take images of those stars over several years, you'll actually see the stars move relative to each other and go around each other. So the idea, if you watch that video, that Crash Course Astronomy, what makes a star a visual binary is actually a little bit fluid because you may have stars that are so close together you can't see them separately visual with the telescopes you have today. But in a few years, you get a bigger, better telescope, and now you can see separate stars. So they aren't visual binaries today, but in the future, they may be visual binaries. So what do we call binaries whose orbital motion can be seen only by their spectra? These are the spectroscopic binaries. So you may have you may have binary stars paired so close together that even with our best telescopes, we can't actually see that they're separate. But as they're going around each other, one of their lights will be blue shifted and one of their lights will be red shifted. And if you see those pairs of lines, that tells you you're looking at binary stars. So what do we call binaries whose orbital plane is such that one star passes in front of the other as seen from Earth? These are the eclipsing binaries. So these are rare because they have to be lined up just right so that their orbital plane is seen kind of edge on from Earth. And when that happens, you will actually see one star pass in front of the other and block that other star's light. So if you look at this diagram here, when you're seeing both stars 100%, you're getting all the light from both stars. You've got a lot of light. And then when one passes in front of the other, while it's passing in front, the light starts to dim, and then one star will be eclipsed by the other. So the light is down, and then the other one starts to appear fully again. It goes up, and so forth like this. So eclipsing binaries are kind of rare. They have to line up just perfectly from Earth for this to happen. But when this does happen, we can figure out extra things about them. By measuring how long it takes for them to pass in front of each other, you can figure out the radiuses of the separate stars. Radiuses, I says, not radii. I don't like irregular Latin plural, but that's just me. So, HR diagrams. Back in 1912, Danish astronomer Einar Hertzsprung. So, throughout most of the world, if you see the letter J, you pronounce it like a Y. So, that's Einar Hertzsprung. And the American astronomer Henry Norris Russell. They were working independently, and they discovered that if you plotted a diagram that shows stars' luminosity versus their temperature, most of the stars would fall along this smooth curve. So this happens occasionally in science where the field has advanced to a certain point and different people working separately will get the same idea and they'll work out, they'll work through the data and they'll come up with the same conclusion. So these guys were not partners, but we named this type of diagram after both of them. And quick aside, Henry Norris Russell, he was one of Cecilia Payne-Gaposchkin's advisors. She had two. One of them was a guy named Harlow Shapley, and Henry Norris Russell was the other one. So Russell is the guy, if you remember Cecilia Payne-Gaposchkin's story, she had this crazy idea in her thesis that said stars are actually mostly hydrogen and a little bit of helium and very little of everything else. And at the time, that went completely against all the astronomical thinking. So Russell was one of her advisors, and he advised her to really downplay that result. That result was still in her thesis, but he told her that that's kind of crazy. I wouldn't, put in a little bit of a caveat when you're explaining that one. And so she did. And then a few years later, Russell, through his own work, found out that actually Cecilia Payne-Gaposchkin was correct, and her very bizarre revolutionary idea was actually correct. And so he did the right thing. He said, well, this is my data. This is what I've got. I found this result, and I'm not the first person to have this result. I actually had a student I was working with years ago named Cecilia Payne-Gaposchkin. I think she was probably still just Cecilia Payne at the time. And she came up with this idea first. And so he totally gave her credit. And for whatever reason, all the astronomical community said, good job, Russell. Great idea you've had, and didn't give her enough credit. So she got kind of robbed there, but that was not Russell's fault. Russell did the right thing. Anyhow, Einar Hertzsprung, Henry Norris Russell made a plot of the luminosity versus the temperature of many stars, and they found most of them would fall along a smooth curve. So this is the kind of curve they got. This is the Hertzsprung-Russell diagram, or HR diagram for short, also called a luminosity temperature diagram or temperature luminosity, although it should be luminosity temperature. You say the y-axis first. Anyhow, you have luminosity on this axis, and you have temperature on this axis. A couple of things to point out about this. The horizontal axis, temperature, is kind of backwards. It doesn't have to be this way, but this is the way traditionally they've done it. So typically, if you're doing an x-axis, you're going to start with the small numbers over here, and the numbers will get bigger as you go to the right. On an HR diagram, that's exactly opposite. You start with the highest temperatures on the left, and the temperatures go down as you go to the right, which is weird, but that's how it's traditionally been done, so that's how we do it. And if you quick scan this graph carefully, you may kind of see the reason why, that we start with the high temperatures and go to the low temperatures. So look up here at the top of the graph, and you'll see some very familiar letters, O, B, A, F, G, K, M. So this is why they plot them this way, so that they get to keep doing it this way. They could just flip it and do it the other way, but we don't do it that way. We tend to do it this way. So yeah, the x-axis is backwards. The y-axis is in the correct direction, for what it's worth. And the other thing to point out is both of these axes are logarithmic. So we do this when we need to cover a huge amount of data and get it on one singular graph. So what that means to be logarithmic, it's easier to see here on the y-axis. Every time you go up one little kind of even mark here, you're not like, this isn't double that one, it's actually 10 times that one. And this one is 10 times that one. So as you go up, just a little bit, if you go up one click, you're 10 times bigger. 2 clicks, you're 100 times. 3 is 1,000, and so forth and so forth. This is because we need to represent a huge amount of temperatures and luminosities all on the same graph. So the temperature one is also logarithmic. So it's easiest to see here going from 5,000 to 10,000. So we've doubled by going this far. And if you go that far again, you haven't gone up another 5,000. You've actually doubled again. So yeah, it's logarithmic. So something to point out about these things. HR diagrams, even though they are sometimes drawn with the stars against a black background, these are not in any sense an actual map of the sky. This is not showing you where stars are. This is showing you their luminosity versus their temperature. And you can make one of these graphs for all the stars in the sky and plot them all along this graph. Or you can look at a particular galaxy or a particular star cluster or some kind of group of stars And what you do is for every one, you figure out its temperature by looking at its spectrum, and you figure out its luminosity, which can be trickier. And then you plot them on this graph, luminosity versus temperature. So in this graph, the hot luminous stars appear on the upper left. So if you're looking here, temperature increases as you go left. So as you're going left, you're getting hotter. And as you're going up, you're getting more luminous. So up here, hot luminous stars. The cool dim stars are on the lower right. So on this graph, as you go to the right, temperature actually goes down, which is backwards, but that's how we do it with these graphs. And the fact that it's at the bottom means that it has very low luminosity. So when you look at a group of stars and you plot them, you get a couple of trends appearing. So let me point out a few things before we talk about the trends. Right here in the middle is the sun. So if we go straight down, remember the sun, the surface of the sun is about 5,800 Kelvin, so that's why it's right about here. And on the luminosity graph over here, the sun has a luminosity of 1. Well, look at the units. The units for luminosity are solar units. So that means the sun has 1 times the luminosity of the sun. Well, that makes sense. If you go up one little hash mark here, you've gotten 10 times brighter. If you go up 2 hash marks, you've gotten 100 times brighter, and so forth going up. And going down, if you go down 1 hash mark, you're 1/10 as bright. If you go down 2 hash marks, you are 1/100th as bright, and so forth and so forth. So yeah, keep this in mind as you're looking at it. The sun is right here. So the main trend you get is what's called the main sequence. So about 90% of stars in the galaxy, in the universe, any large collection of stars, 90% of them are going to appear on this slash going top left to bottom right. This is called the main sequence. So all these guys on this big slash are called main sequence stars. It's kind of a weird use of the word sequence. It doesn't have anything to do with time. It's not that they're starting here and ending up down here, or starting down here and going up here. It's still called a sequence. This is the main sequence. So on the main sequence, the hottest ones, so the ones all the way to the left, are the most luminous. They're the highest on the graph. And the coolest ones, all the way on the right, are the least luminous. They're at the bottom of the graph. So yeah, that's the main sequence. So you have a few stars that kind of buck this trend. So you have some stars that are cool, so they're over here to the right of the graph, but they're very luminous, so they're very high on the graph. So stars up here like Aldebaran, Antares, Betelgeuse, all these guys, these are up here. And then you have other stars that are very hot, so they're to the left, but they're very dim, so they're towards the bottom. So guys down here, Sirius B, Procyon B, stars like this. So these should be a little bit surprising. Look at these guys first. So these guys are cool. So you would think, all right, well, they're cool. Well, they shouldn't be very luminous, but they are very luminous. So these guys are way up here. And these guys, the opposite is true. They're very hot. So you would think they would put out a lot of light, and yet they're not very luminous. They're at the bottom of the graph. So what is it that makes these stars different? Well, to understand this, you have to bring back this idea. Remember a few slides ago, well, kind of many slides ago, we did the Stefan-Boltzmann law. So this is a law that relates luminosity to the radius of the star to the temperature of the star. And 4 and pi and sigma here, these are constants. So this is the key to understanding the difference. So if you have a star that's in the top right, so these guys up here, Aldebaran, Antares, Betelgeuse, guys like this, they have the same temperature as stars that are directly beneath them. So there's not a red giant on this graph that's directly above the sun, but okay, let's say like Antares here is pretty much about the same temperature as Barnard's star down here. Barnard's star is weird because it has the highest proper motion of any star. It seems to be racing across the sky as far as stars go. Not really racing, but going faster than other stars. But yeah, anyhow, Antares and Barnard's star both have about the same temperature. You look at them, you do Wien's law, you figure out the temperature, and they're about the same. But Antares is about 1/1000th as bright as the sun. I'm sorry, Barnard's star is about 1/1000th as bright as the sun, whereas Antares is almost 100,000 times as bright as the sun. So how is that? Well, Antares is much bigger. T is the same in this, but for it to have a much higher luminosity, its radius must be much bigger. Antares is a red giant star. So most of the giant stars, the very big ones with big radii, these are cool, and therefore they're red, and so we call these red giants. I mean, what else are you going to call them? So Antares and Aldebaran, these are both cooler than the sun, so they're to the right on this graph compared to the sun. So the sun is here, and those guys are to the right of where the sun is on this graph. So they're cooler, which would make you think they should put out less light, but they put out a lot more light because they're much bigger. So Aldebaran, cooler than the sun. Aldebaran, if we're looking at this, probably about 4,000 Kelvin. The sun, again, is 5,800 Kelvin. But Aldebaran is more luminous than the sun because it's so much bigger. Its radius is about 30 times bigger. So if the sun is this big, Aldebaran is huge compared to the sun. So that's how it's more luminous, even though it's cooler. If you look at the stars on the lower left, these guys have the same temperature as the stars that are directly above them. So we'll compare Sirius B to Spica. So both these guys are over 20,000 Kelvin. But Sirius B has a much lower luminosity than Spica. Spica is about 10,000 times as bright as the sun. Sirius B is less than 100th the brightness of the sun. And the reason that is, even though they're the same temperature, is Sirius B is much smaller. Sirius B is a dwarf. So we'll talk about dwarfs in the next chapter where we deal with the lives and deaths of stars. White dwarf is what happens when a kind of low mass star dies, in a sense. You end up with a white dwarf. That's what Sirius B is. So yeah, these stars are very, very hot. They're actually the core of a once living star. So they're very, very hot. But they're way smaller than ordinary stars like the sun. So on this graph here, the big yellow circle that's kind of indicated by, we're only looking at part of it here, is the size of the sun. Here's the tiny little Earth. It's only about 1/100th the radius of the sun. And a white dwarf star would be about the same size as the Earth. So we call it a white dwarf star. Technically, it's a dead star. More on that next chapter. But these guys are tiny. So they're very, very hot. They're way over here. The sun, 5,800 Kelvin. This guy, 22,000 Kelvin. So about 4 times as hot as the sun. But way less luminous because it's so much smaller than the sun. So to review, what do we call this graph? We call this the HR diagram or the Hertzsprung-Russell diagram. And what do HR diagrams compare? On the y-axis, you have the luminosity, and on the x-axis, you have the temperature. And both of those scales are logarithmic, so that you can cover huge ranges of things. And for reasons of tradition, and so that we can keep the "Oh, be a fine girl, kiss me" thing going, we do the temperature scale backwards. So big temperatures on the left, and the temperatures get smaller as you go to the right, which, as a math-loving person, that seems very backwards, but that's how we do this one in astronomy. That's it for this part. Hopefully you guys found that interesting.